Hello, and welcome back to another episode of What the Hack. We've learned a ton of basic concepts in programming and computer science. So in this video, let's change gear and talk a little bit about what's going on underneath the surface of our code and behind our programs. It is fairly easy for us to remember the text and numbers that we see, but how does a computer remember the number and text that it sees? They use binary. Binary is a number system with only two digits, 0 and 1. Each number takes up one bit, which is the most basic unit of memory storage in computers. Inside a computer, imagine bits as little switches that turn on a light that can show us something. Whenever a bit takes the number 1, then the switch will turn on the light, and we will be able to see the thing that's hidden. Whenever a bit takes the number 0, then the switch turns off the light and the thing stays invisible to us. But one bit can only be a 1 or a 0. What if we want to store the number 2 in our computer's memory? This is where something called bytes come in. 8 bits grouped together is called a byte. And with a byte, we can have 8 binary numbers together. Imagine a byte as 8 switches lined up together. Now that we've got a byte, we can store much more information with zeros and ones. Let's take a look at how bytes are used to store and represent numbers. The reason why this is called binary is because in Latin, bi means 2, and this number system consists of only 2 digits. Binary numbers in a byte have a base of 2. And from right to left, we will raise 2 to the power of from 0 to 7. The result of 2 to the power of a number is what the light can show us if it's switched on. The rightmost switch has 2 to the power of 0, which is 1. The second rightmost switch has 2 to the power of 1, which is 2. The third rightmost switch has 2 to the power of 2, which is 4, and so on. And the leftmost switch has 2 to the power of 7, which is 128. The numbers that the switches show are the numbers represented by each bit in a byte. So the rightmost bit in a byte represents 1, the second rightmost bit in a byte represents 2, the third rightmost bit in a byte represents 8, and so on. Now let's take a look at how to represent binary numbers in a byte. First, how do we represent the number 2? It's fairly simple. We see that the second rightmost switch has the number 2, so we're going to turn that switch on and keep all other switches off. And as we know, switch on means 1 and switch off means 0. From right to left, we have one switch turned off, then one switch turned on, and all the other switches turned off. So we're going to write 0 for the rightmost switch, 1 for the second rightmost switch, and 0 for all the other switches. This sequence of number is the binary representation of the number 2 in a byte. Let's take a look at a much more complex example. Say we assign the integer 44 in a variable in Python. So our computer needs to store this integer in a byte. What should we do with the switches that we have to have this integer 44 stored and represented? Reversely, we begin by looking at the switches from left to right. The leftmost switch has 128. It is much, much bigger than our number 44, so we don't need it. Let's turn it off. The second leftmost switch has the number 64, which is still bigger than our number, so let's turn it off. The third leftmost switch has 32, which is smaller than our number 44, so we will keep the switch on. Now that we already have 32, how much more do we still need to make 44? We can find that by subtracting 32 from 44, which gives us 12. And we will take this number 12 and continue from the fourth leftmost switch. The fourth leftmost switch has 16, which is larger than 12, so we will turn it off because we don't need this much. The next switch has 8, which is smaller than 12, so let's keep it on, and do 12 minus 8, which gives us 4. With 4, let's move on to the next switch. The next switch has 4, which is the same number as what we have left, so let's keep this switch on, and we have 4 subtracted by 4, which gives us 0, meaning that we don't need any of the following switches anymore, so let's turn them all off as well. Now for the switches that are turned off, let's write zeros next to them, and for the switches that are kept on, let's write ones next to them. And ta-da! This is the binary representation of our number 44. This number reads 0010 1100, which looks so different from our number 44, right? If we see such long strings of zeros and ones, we might have a hard time understanding it, but when our computers see it, they can understand it right away. Let me show you what I mean. Suppose we have a number 011000100. What number does this group of zeros and ones represent? Let's take a look at it with switches. First, we will line this group of zeros and ones with our switches. and turn on any switch that has a 1 next to it while keeping the other switches off. We can see that the second leftmost switch is on, and it has the number 64. Let's keep 64 with us. Next, we see that the third leftmost switch is also on, which is the number 32. So let's add 32 to 64, which gives us 96. Moving on with 96, we see that the third rightmost light is also turned on, and that is 4. So let's add 4 to our 96, which gives us 100. Do we have any more lights that are still on? No, and it means that we're done with our calculation. So what does this group of binary numbers represent? It represents 100. In my opinion, this binary number looks very, very different from the 100 that we usually write in the decimal number system. And that's because it took us a while to calculate and understand that it actually means 100. But because computers are so good at doing calculations like this, they can understand that it means 100 and not even a blink of an eye. I wish I could calculate as fast as a computer. Now that we know how computers represent numbers, what about letters? Magically, alphabets are also represented with binary numbers in our computer. A system that alphabets are represented in is called ASCII. ASCII stands for American Standard Code for Information Interchange, and it's one of the character encoding systems that our programming languages use to convert strings of characters into binary numbers. For each character in the English alphabet that we see, lowercase or uppercase, there is a specific and unique integer associated with it. For example, the uppercase letter E has the integer 69 associated with it. And if we go through the binary conversion with our light switches, 69 is represented in the binary number like this, 01000101. So when we store a string with the uppercase E in Python, it would be stored in our computer memory as the binary number. Here comes a problem. When we want to retrieve or take out this string of uppercase E stored in our computer's memory using our light switches, we know that 01000101 actually means the integer 69. How can Python tell us that we wanted the uppercase letter E instead of the integer 69 from this string of binary numbers? This is where ASCII comes to play. ASCII values associates the integer 69 with the uppercase letter E, and whenever Python wants to retrieve uppercase E, it will actually retrieve the integer 69 from the binary number string stored in the memory first, and use the ASCII table to translate this integer 69 back to uppercase E. This can easily happen because we know that computers can scan through and process a lot of information very, very quickly. And the integer 69 in the ASCII table is only associated with uppercase E and nothing else. So whenever we have this integer, 69, when we are working with a string, Python will always know that it's uppercase E that we're looking for. When we store information in a string, we often store more than just one English alphabet. If we are chatting with our friend and we send them a haha message, how would this be stored in our computer's memory? Let's try it out with our ASCII table. The uppercase letter H in the ASCII table is associated with the integer 72, and 72 in binary representation is 01001000. Firstly, we will put down these binary numbers. Next, the lowercase a in the ASCII table is associated with the integer 97, and 97 in binary representation is 01100001. Let's put this binary representation next to the number for uppercase H. Next, the lowercase h in ASCII table is associated with the integer 104, and the binary representation for 104 is 01101000. Let's put this next to the long number that we already have. Lastly, we know that lowercase a is 01100001, so we can put it at the end. This super long string of binary numbers is how our message haha would look like in our computer's memory. If we use Python and we want it to interpret this binary representation as an integer, it would be 1,214,343,265. That is a super big number. But because we know it is a string of our haha message, Python will actually cut the long binary number into 4 bytes and convert each byte of binary number back to the decimal number system, and use the ASCII table to find the alphabet that corresponds to that decimal number. And this is how Python, our programming language, will use tools like the ASCII table to translate characters to integers and convert them into binary numbers for the character to be stored in the computer's memory. And reversely, to retrieve a character back from the computer memory with the help of binary numbers. Now that we've learned the basics of how the information that we have in our programs can be stored in our computer's memory, let's take a second to appreciate how our programming languages and computers can work and process so much information so quickly. They are awesome. And what's more awesome is that you're learning programming to be able to communicate with our computer and have them help us with processing the huge amount of information that we have in our daily lives too. That's all for this episode. We hope you've come to understand how the information that we have are represented and stored in our computers. And don't forget to check out the challenges where you can use what you learned today to solve some fun problems. See you guys in the next episode. Be sure to like, subscribe, and don't forget to follow us on all our social media. Thank you.